We will now see how we can free a circular list. So say we have this function and we have a list pointer and we create a list node. So S, it's this box and it points to a list node. So we say it points to this one. And then we add 2 more nodes, and then we want to free this list. That means all of this. Okay, so there are different alternatives to freeing a list. One is, as we do here, namely to give the address of this pointer, and the idea is that this will become a null pointer when we return from free list. Alternatively, we may skip this ampersand and write like this. I mean, it for a different function, and this function will then leave the value of S to an invalid pointer, and we have to set it ourselves to null afterwards. So that's a matter of taste or matter of what the API should look like. Okay, so one first approach, which is wrong, would be to, well, first of all, we need to check when we have returned back to S. So we will here we start there, and then we will do something there and something there, and then we will notice that we are back to S. Okay, so if we start freeing this node and then move on to the next one and to the next one, and all the time check that we are have not returned back to S, then it's actually invalid code. And the reason is that we cannot use a pointer, not even compare with equality or inequality once we have freed what it points to, because when we have freed something, the value of the pointer becomes invalid. So if we just look at this P here, it's a pointer somewhere, and when we free what it points to, we cannot use P. So doing like this, if P, I mean using the value of P that we have just freed, that's invalid. Okay, but what we are allowed to do is to overwrite P with a new value, so that P becomes a valid pointer again. That means we should not start with freeing the first node and then comparing if we come back, but instead what we do is to, well, the first thing that we do is to so what we put here as the argument is the address of S. Okay, and that is S is a pointer to a list, so the address of S is a pointer to a list. So the parameter here, it points to that one. So here is head. Okay, and the reason that we want the pointer to S is that we want in the end here say that it should be null, and then of course we need the address of this local variable. Okay, but it's tedious to use star head all the time here, so therefore we copy what head points to, namely S, into this variable. So h equals star head means we put h, we set h to the same value as s, which means we put h, when we draw this, we put it, okay, we can make a box for h, and it will be the same content as s has, namely a pointer over there. But it's easier to write h there, so we know it points there. Okay, so the first thing we do is to check if this is a null pointer, because then we shouldn't do anything. And then we say p is the successor of h. So let's say it's this one, so we set p there. Okay, and then we loop until we return to what h points to. And we say q is the next, so we set q there. And then we can free what p points to. So we free this. We don't free the string because, well, I mean, if somebody puts something in a list, it's not, it may be put there because it's waiting for something, but should not be destroyed when we don't need the list any longer. Okay, so we have freed the list node, and then we move p to the next by copying it from q. So now both p and q point to the same. Okay, we check if p has come to h, and it hasn't, so we do the same again, meaning we give a new value to q, so q is there as well. And then we free what p points to, so it doesn't exist, and then we copy p so that it points to the same as q. Okay, and then we come back here, and we see that now p is equal to h, so we can free this one as well. And then we set what what head points to null. Okay, head points to that one, and we set it to null. So now s has become null. Remark about free. Say we have two pointers, a and b, and we let here a point to data for this int, and we say that b should point to the same. Then we can free a, that's fine, and nothing special happens, except what is happening is that both a and b become invalid after this, since the data no longer exists. Well, we have this int, and we have a points there, and b also points there. Okay, and then we free this box. Okay, and then we say that what p points to should be 12. That's a bad idea because it doesn't exist. Now we come to something which looks harmless but is not. Namely, just thinking about h is wrong, or thinking about b is wrong. Well, not thinking, but just mentioning, or in the strict C terms, evaluating an expression which reads the value of this variable is wrong. And it's very wrong because even anything can happen. The computer may explode. That's very unlikely, but it's permitted by the ISO standard, unless prohibited by national law, perhaps. Anyway, the program can crash. That's what I was going to say. And that's the reason why we are not allowed to start with freeing h and then going back to see if we come to this. What would actually happen? Probably not much. H is typically put in a CPU register, and it's just an integer register, so the machine will not notice but for some machines it can make a difference, so it's not permitted. And it's good rule to never use an address that is invalid.